Welcome to part 2 of task 4.3. You've explored the concept of a rational function, but I want to introduce you to the parent function. This is the parent rational function. Right here is that equation, parent equation, 1 divided by x. We're going to complete a table, complete a graph, and talk about some of its features. So let's start off by plugging into this equation and creating a table. So I'm going to just plug in these standard points to kind of fill in a general shape of this function. So f of negative 2 is 1 divided by negative 2, which is negative 1 half. 1 divided by negative 1 is just negative 1. 1 divided by negative 1 half is just like multiplying by the reciprocal, so it's actually 1 times negative 2 over 1, or negative 2. 1 divided by 0, we can't do that. That is the one thing we can't do with our rational function, so we're going to call that undefined, and we're not going to graph anything there. And we're actually going to see that create an asymptote in just a little bit. So 1 divided by 1 half, I'm going to keep going. Again, that's like multiplying by the reciprocal, so it's like doing 1 times 2 over 1, so that's just 2. 1 divided by 1 is just 1, and 1 divided by 2 is just 1 half. So let's go ahead and plot these, and I'm going to try to plot them as precisely as possible. Our first point, we're going to go over to negative 2 and down to negative 1 half. Our second point, we're going to go over negative 1, down negative 1. Our next point, we're going over negative a half. I know that's not a normal point we would plot, but it just really shows us the shape of the curve. So over negative 1 half, down negative 2. And now we see undefined. That next point we see pretty blatantly as undefined. Well, what is that going to represent? In this case, that's always going to represent an asymptote. So I'm going to draw that asymptote in. Essentially, nothing is ever going to be able to be plugged in here. That whole thing is undefined. So I'm going to draw a dashed line straight through 0, saying that this is undefined. It's never going to touch the x-axis. It's never going to cross the x-axis. It's just going to keep getting closer and closer to it, doing some funky, weird things. So I'm going to connect the dots that I have so far. I know that this is going to get closer and closer to my asymptote, so that is going to go straight down forever and ever and ever, getting closer and closer to the line. Okay, let's keep plotting what we've got. So next up, I'm going to plot over 1 half up 2. Again, maybe not a standard point you would have done, but it's really going to show us the shape of the curve. Over 1 half up 2. Then I'm going to go over 1, up 1. Followed by over 2, up just 1 half. Hopefully you're feeling like this is kind of mirrored in a weird way. It is. We're seeing these points reflected. They are familiar to each other. And just like the opposite end, just like this end, which is going to follow that asymptote all the way off the graph, then the upward end is going to do the same thing. So I'm going to get closer and closer and closer to this asymptote and just head off the graph in that direction. So now where do we go from here? Where do we go from here? Well, 1 over x, as I think about plugging in whole numbers, I plug in 3 and that becomes 1/3. I plug in 4 and that becomes 1/4, slightly smaller. I plug in 5 and that becomes 1/5. I plug in 6 and that becomes 1/6. 7 becomes 1/7. 8 becomes 1/8. So again, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th. If I plug in 100, that's 1/100th. What is the shape we're seeing here? Well, we're seeing it approach the x-axis but never quite get there, because even when we're out at 1,000,000, it's going to be 1 over 1,000,000, which is not zero. It's so tiny we're going to think it looks like zero, but it's not zero. Well, what is this concept of a number that gets smaller and smaller and smaller and smaller and closer and closer and closer and closer and closer to zero without actually touching zero? It's another asymptote. So we do have another asymptote here on the x-axis. And it's going to do the same exact thing in the other direction. It's going to get closer and closer and closer to that x-axis without ever touching it. So it's going to head off the graph, getting closer and closer to zero on both sides. This is the parent rational function. This is the parent rational function. You'll see it never touches either axis because both the x and y axis are asymptotes. Again, here is an asymptote on the y-axis, and here is an asymptote on the x-axis. So let's fill in some features of this function. If I'm talking about domain, I'm saying what x values do I see here? Well, I do see an arrow heading out to negative infinity, and I do see an arrow heading off to positive infinity. So I do think it includes all numbers, negative infinity to positive infinity, but there's a problem. We've got this asymptote right through the middle. We can't equal zero. So we're just going to remove zero. So it's all numbers, negative infinity up to zero, and then all numbers 0 to infinity. We're just excluding 0 from our domain. Let's do the same for the range. Well, I see this arrow down here indicating that it does start way down at negative infinity, and I see this arrow up here saying that it does go off to positive infinity. So again, I think I'm encompassing all numbers. I think my range does go from negative infinity all the way to positive infinity, but I have this asymptote right here in the middle. So when I'm thinking about all of this, I have to stop right here at 0 and then pick up and keep going after 0. So we are really excluding 0 from the range also. So our domain and range really is just all of the numbers except for that asymptote. So the domain, all those x values, everything extending in this direction and this direction, just not that asymptote right in the middle. Same for range. All of these numbers extending down to negative infinity, all of these numbers extending up to positive infinity, just not that asymptote across the middle. So is this function continuous? No, it's not continuous. It's got these big asymptotes right through the middle, which cause it to stop, to break. That's why it almost looks like two separate functions. It looks like this function over here in the third quadrant, and then a separate function up here in the first quadrant. Don't be fooled. This is still just one function. It's just broken right in the middle. And does it have any intercepts? Well, we've already established that both the x and y axis are asymptotes, so it'll never touch the x-axis, never touch the y-axis, so no. And I'm going to actually clarify that down here by saying x equals 0, y equals 0 are both asymptotes. So lastly, let's check out end behavior. And I want to write the end behavior out for us so we know what we're expecting. As x goes to negative infinity, our function f of x goes where? Well, as we go over here to negative infinity, that function is flatlining. It is just flatlining straight to the x-axis. Well, what y value is that? What y value is flatlining right to the center? That's 0. And now let's check out the other direction. As x goes to positive infinity, f of x goes where? Well, as we go this way to positive infinity, my function is also flatlining. It's flatlining to the x-axis. So what y value are we talking about? We're talking about 0. So the end behavior on both sides really is just looking at these two arrows right here, which are flattening out and heading to 0. So let's talk about really quickly, what about this is a feature of rational functions? Well, asymptotes will always appear in rational functions. Most of the time, we will see both a vertical asymptote, meaning one going up and down, and a horizontal asymptote, one going left to right. We will see both horizontal and vertical asymptotes for the most part in rational functions. Now, once we start translating our rational functions, shifting them left, right, up, down, we will see some intercepts. We will definitely see some intercepts, but they will never be continuous. We will always find it broken somehow by these asymptotes. So look for the domain and the range and the intercepts to change. Look for those to be slightly different as we shift the graph left, right, up, down. But for the most part, we're only going to see our graph broken, or our graph um, having these oddities wherever the asymptotes are. And that's what we're going to explore a little bit later in this module. We're going to explore how to figure out where those asymptotes are, how to figure out where those intercepts are, how to figure out that domain and range. So all of that is coming. But for now, I want you to just see what a rational function looks like. You'll get to try an example of this one on your own. Start by plugging in to the equation just like we did. Plug into that equation and then determine where does your graph kind of boomerang off towards positive and negative infinity. That is one of your asymptotes. And then once the graph is all done, look back at it and determine, where does my function break? That's going to be where my domain breaks. And where does my graph go to at either end? That's going to be your end behavior.